So notice I see this 1-to-1 ratio, and I really don't see anything else down here. What I'm going to show you is how this is formed. Okay, so again, recognize bromopropane. Okay, what type of electrons does bromopropane have? It has sigma bonds, and it has non-bonding electron pairs, right? So according to what I shared with you, which electrons should we remove? Which are going to be the easiest electrons to remove? Sigma bond or non-bonding electrons?
Non-bonding.
Non-bonding. Okay? So again, that's what I kind of want you guys to realize here. So notice I have with one bromopropane, okay? So once I have one bromopropane, recognize that I have two isotopes, 79 and 81. But notice that I'm removing the electron off the non-bonding electrons to make that radical cation. Okay? Once I've done that, if I break this bond heterolytically, notice I'm using an arrow with two electrons, right? Double arrowhead. I make a carbocation. And this carbocation is 43. Okay? So notice this, again, in the mass spectrum, I want to re-emphasize this. Again, is any peak that shows up in the spectrum has to be a cation. And again, there's two cations, either a full positive charge or a radical cation. Okay? So what cation is associated with 122, 124? There it is. This is the radical cations of loss of an electron from a bromine non-bonding electron pair. If I break this bond heterolytically, then I should see a peak at 43. Do I see a peak at 43? Yes. Okay? Now, you could determine how to proceed with these mechanisms, but again, I'm not going to show that right now. Again, I wanted to focus on that, but eventually you should be able to do that. A question I will ask you is I'll give you guys a spectrum with a molecule, and what I'll do is I'll give you guys specifically numbers that I want you guys to showcase how that molecule, what is the speed, what is the structure of that ion, and show me the mechanism of how it's formed. Okay? So again, let me go through this, it'll make more sense. We'll do an example. I put an example on this PowerPoint. So here's the mass spectrum for 2-chloropropane. Again, 2-chloropropane is not going to be that different from bromopropane in that we're still going to remove that electron off the chlorine, right? Because the chlorine is the only species that has non-bonding electrons. And if I do that, I should get a radical cation that has two chlorines in the ratio of 2-to-1. Okay? So here it is here. Okay? So if I basically remove this electron here, I make this radical cation. Okay? This radical cation with chlorine, with the radical on chlorine, the positive charge, okay, is 78 and 80. If I break this bond heterolytically here, I get this carbocation that has a mass of 43. And again, if I go back here, you can see the mass of 43. Now recognize this 43 is my base ion peak, but notice that I don't see the 3-to-1 ratio. Why don't I see the 3-to-1 ratio? Well, in that ion that's formed, it has no chlorine. So because it has no chlorine, I don't see it. Okay? So notice that, again, we're going to measure this. We're going to see this. We're going to see this. I don't see chlorine dot. Because chlorine dot is neutral, I will not see a peak for that mass. Because chlorine dot goes through the instrument undetected because we're detecting only specifically ions that are positive. Okay? Here is another mechanism. Okay? And again, I'll show this in a moment. But if you take an electron on the chlorine and push it here, and if you break this bond homolytically, okay, so what do we mean by homolytic? Homolytic means that we're breaking the bond where the sigma bond, one of the electron goes onto one carbon in which it was bonded, and the other electron goes down into the other one. So if I break this bond homolytically, I get methyl dot, shown here, and I get this species here. So recognize I could break this bond homolytically, and so the result of that is basically a peak at 35 for this molecule, I'm sorry, 63 and 65. And the reason I see the two isotopes here is I still have the chlorines attached. So again, that permits me to determine why I see this 3-to-1 ratio. Okay. Now, I will talk more about this mechanism, but please write this down because we'll get to it in a while. This is called alpha cleavage, and alpha cleavage is one of the more important mechanisms in this transformation. Okay. Recognizing alpha cleavage, I'm moving radicals. So because I'm moving radicals, the arrows I have here are single arrowhead, as opposed to up here where I'm breaking the bond heterolytically. Okay, so one of the things I'm going to try to share with you is when do we break bonds heterolytically as opposed to homolytically. Okay. Now, recognize that the reason these form in relatively good amounts, okay, is I want you to remind yourselves that this is a species that's a stabilized carbocation. If I was to push this electron on this double bond towards chlorine, I make a carbocation here. So this is a resonance stabilized carbocation where I place the charge on chlorine. And recall, if you learned resonance early on in the first semester, any resonance structures of carbocations in which you have a resonance structure where everything has a full octet is always better than having a carbon with just six electrons around. Okay, so this is the better resonance hybrid form of those carbocations. Again, you'll see that in an example. I'll do some more stuff on the document calendar. Okay. So a little bit more about fragmentation. Again, the molecule absorbs additional energy. Okay. The extra energy places the molecular ion in an excited vibrational state. And again, the molecule dissipates its energy by breaking into fragments. Okay. Give me a couple more slides and we'll call it quits for today, because I know it's almost time. Fragmentation generally occurs by unimolecular processes, and one of the things I want you to realize is the way molecules fragment is very predictable. You've learned a lot of chemistry in 220A if you took it here, and that you learned the general stability of carbocations is in this fashion. Methyl carbocations are the least stable, primary a little bit more stable, secondary, tertiary, and then you learned about allylic and benzylic carbocations. So in general, any process that makes these types of carbocations are always going to be favored than these guys here. Okay, so ions detected are either cations or carbocations, and so the fragmentation will rely on the stability of the carbocations formed. Okay, so carbocations that are formed that are more stable are going to form in highest amount. Okay, so this gives me the first example. Cleavage of a radical cation occurs to give a radical, but only. Okay, so let's look at an alkane. Okay, so in this alkane, again, if I have a hydrocarbon here that's just an alkane, I only have sigma bonds. Often, and Sorel does this, he'll show the radical cation in this fashion. The difference I'm asking you to do is specifically show me where we lost that electron. Show the bond. Okay, because if I see this is what your textbook's referring to, but in essence, we're doing this. Why is this better? Because now, recognize if I push the arrow this direction, I get a carbocation plus methyl dot. Okay? Now, obviously, I won't measure methyl dot, but I'll measure the carbocation. Okay, so let's kind of see an example of that. Here's the spectrum of hexane. Okay? And so hexane this is a molecular ion peak, and I can lose all these different fragments. So let's see if we could see what's going on here. Okay. So again, recognize in methane, hexane, what I want you guys to do is convince yourself that you would fragment all these by basically taking an electron from this sigma bond. If I take the electron from this sigma bond and push it in that fashion, I would get this one. But then I have the choice. Why didn't I choose this sigma bond? If I choose that sigma bond to lose electron, I would get this fragmentation. This one here, I would get that one. And also remember the direction. Okay? So again, go through this series and try to break that sigma bond and see how it fragments, either in this direction or that direction, and you should get this one here, okay? If I break it this one, take the electron from this sigma bond. If I move the electron in this fashion, I get this and this carbocation. But if I move the electron in this fashion, I get this radical and the ethyl carbocation. And notice that's explaining all this. Okay. Last one. This is neopentane, and what neopentane is a carbon that has 4 methyl groups around it. So this is the structure of neopentane. Notice neopentane, we don't see the molecular ion peak. Okay, so this is an example, and I just want to finish off here in that this is an example of a structure where you can't see the molecular ion peak. So this molecule here, if I wanted to see that, I would have to do chemical ionization. So the question is why? Well, recognize if I remove the electron from the sigma bond here, very rapidly, it wants to break heterolytically to make this carbocation. And remember, tertiary carbocations are one of the more stable, and notice that's my base peak. So the reason we don't see the molecular ion peak for neopentane is as soon as we bombard electrons, it dissipates energy so fast by breaking that bond and making the more stable tertiary carbocation. Okay? So I will continue on with this on Monday, and again, I should have this all finished on Monday, okay?